Before we get to the last topic in Chapter 4, just to recap or quick capture of the last two sections, our true-false moment. So I will leave this here for a few seconds, let you pause, capture this somehow. I did cross those two problems out, didn't like them on purpose. And here comes the answers. All right, so the first 6 sections of Chapter 4 are now behind us. The homework's out there. We're skipping sections 4.7, 4.8, and then this last section, 4.9, is a fun application of the word vectors and matrices, something called Markov Chains. So let me just jump right in and start an example with you guys, and we'll explain what's going on in a bit. So let me start out with a matrix. We're going to multiply it times a vector. And we could probably do this one in our heads. Again, row by column, so 0.5 times 1 plus 0. Second row, same column, 0.5 plus 0. Okay. Next, I'm going to take that same matrix and we're going to multiply it this time by the answer we just got. And we're probably still okay in our heads. Let's do this. So that would be 0.25 plus 0.40. And then 0.25 plus 0.10. Let's do that one more time. Same matrix. And we're going to multiply that times that last answer we just got. And you might need a calculator this time. This gets a little nuttier in our head. It just turns out you're going to end up with this. So let me explain what's going on here, and this is where the chain term comes from. We took this standing matrix, had some initial vector, and it produced a second vector, and then that became the next input to give us an output, the next input to give us an output. That's the chain of vectors, and that's why they call it a Markov chain. Not sure where the term Markov came from. Looks like someone's name, but the chain idea is what I'm asking you to look for. Now, that doesn't mean anything to us right now, but I do want to show you a feature that our calculators can do right now. So with our calculators on, so get to our matrix. Let's edit matrix A, and that's going to be this first guy. So now let's also edit a second matrix, B, and let's make that be my initial vector. So I need a 2 by 1 and 1, 0. Okay, so again, easy enough to ask my calculator to do this, but I'm going to show you a feature that's pretty powerful that takes this chain idea. It's perfect for our calculator. So let's just ask the question, what is matrix A times matrix B? Before we hit enter, I want to store that into a new matrix. My store button is down here next to the 1. Hit that once, a small arrow pops up, and I want you to go grab matrix B again. What we're asking our calculator to do is to multiply a matrix times a vector, and what that answer is my new B vector. Notice he'll now take the place when I do this again. So let me show you what that looks like. My first answer should be 0.5, 0.5, and it is. I don't need to, I'll bring it up again. If I just hit second enter, the same, remember now my B has gone from 1, 0. My calculator now knows it's 0.5, 0.5. So now we're going to ask this question by hitting enter. Yay us. And one last time, I should get 605, 395, and we did. So this is a powerful thing to know about your calculator, how to set up a chain just by giving the initial setup, storing into the second matrix, and you're off and running. So let me give you a few terms that are showing up here. First of all, there is something called a probability vector. And that's any vector that has non-negative entries that add to 1. So, a couple of examples, 0.7, 0.3. Non-negative, add to 1. You could have more than 2 entries. So the vectors can be as in any R space. Again, 0.2, 0.3, 0.5, add to 1. In fact, you could even have a very simple one like this. 1 plus 0, it's all good. And one other thing, we need to identify something called a stochastic matrix. Is a square matrix whose columns are probability vectors. So let's look back at the problem we did. It turns out this matrix is a stochastic matrix. It's square, and its 2 columns are probability vectors. They both add to 1. In fact, my initial vector was a probability vector. Oh, and by the way, my outputs were also probability vectors. So every column you see in the original problem, the columns, the entries add up to 1. So just kind of interesting. We're just kind of making note of that. So let's look at a final example, and this will be the end of part 1. Just to help explain, what's a story that we could attach to this? So let me give you a stochastic matrix, and the story behind this is weather. And I will explain this in a second. So I've got my setup here. Okay, so let's say the weather in Butte County in the last 2 weeks of April can be classified as either good, indifferent, or bad. And in this time of year, you could say on any given day, if the weather is good, the next day, the probability of it also being good is 60%. So notice I'm going from a good day to a good day. That's why I put it in this column. Also, if a day happens to be classified as good, there is a 30% chance the next day will be indifferent, I, which leaves a 10% chance that a good day turns to a bad day on the next day that follows. So notice I'm going to have 3 complete columns, and how we're setting this up is asking what was the weather like on one given day, and then what's the probability it either stays the same or turns to a different weather day. So here's the rest. What's the probability indifferent turns good? 70%. And then I'll say 20% it stays indifferent, 10% it turns bad. The probability of bad day then turns good, 30%. Bad turns indifferent, 30%, which leaves a 40% bad stays bad. All right, so I'm going to give you what we're going to call the initial state vector. And what that's saying is, if you give me the probability that a day is, we're going to call this out in the future, there's a 40% chance we're going to have a good weather day, there's a 60% chance it's indifferent, and there's no chance it's going to be bad. And let's say this is on a Monday. I'd like to know, can we predict, using our forecasting model, what's the weather going to be like 2 days later? Let's say on a Wednesday. So, here we go. We are going to run a Markov chain, starting with this initial matrix, let me just call it P, times my initial state vector. I can call that x sub 0 for my initial one. And we're going to get an output. And that would be Tuesday, which I'll call, that would be x1. And then we're going to do that one more time where x1 would sit here and produce a second vector. And that will be my Wednesday. So let's turn to our technology to help us here. So here we go. Now a 3 by 3. Quick scan, that looks good. All right, back to matrix 2. This is now a 3 by 1, and my initial state was 40%, 60, and 0. All right. Well, I've already set this up. If I hit second enter, the last thing we were doing was this. So my chain is set, and so here we go. We know what Monday looks like. There's Tuesday. Let me go ahead and write that down so we keep track of these. So if that was Monday, Tuesday, and if I do it one more time, we got it. So let's interpret this. So if on any given day there's a 40% chance the weather's good, 2 days later that probability goes up to almost 60% chance it's going to be good. Whereas if there's a 60% chance the day is just indifferent, that drops to about 27% of being indifferent 2 days later. And if there's a 0% chance of a bad day, it rises to 13% chance later on. Quick homework note. You may be asked to write your answer as a percent, like to the 10th or the 100th or 1000th place. So this top number, we would write 49.4 inside the box, and there's a little percent sign on the outside. Also be aware, you may be asked what's the probability of an event, and if that's true, you just leave it in decimal form. So be aware of the verbiage here, probability versus percent.